7b. The table below gives the values of 7 observations of bivariate data x and y. Part 1. Calculate the value of the product moment correlation coefficient and explain why its value does not necessarily indicate that y equals to c plus dx is a suitable model for the data. So to do this, I will go to my trusty graphing calculator, which has been giving me admittedly a little bit of trouble today, but hopefully it won't in the future. And I go to Stat, Edit, and I key in my data for x into list 1 and data for y into list 2. So I've done that already, so you don't have to watch me painstakingly do that. Then I exit, I go back and I ask it to calculate the linear regression line a plus bx. And if you recall, x was in list 1, y was in list 2, so this is all fine, and I just tell it to calculate that. And then it comes up with all of this data, and the one I'm interested in, of course, is the value, is the value of r here. So I go back and I can say that r equals to 0.96953, which is approximately equal to 0.97023 SF. So generally this is a pretty good value because it's very close to 1. However, this isn't enough. Although it is close to 1, we should look at the, it doesn't mean that a linear model is appropriate. Why? Because there could be a curvilinear relationship between the points. So we should always check the scatter diagram. So therefore, we should check the scatter diagram first. Okay, so that explains it. Part 2. Explain how the product moment correlation coefficient can be used to decide for this data whether y equals to a plus b ln x or y equals to c plus dx is a better model, hence determine the equation of the suitable regression line for the above data. So what we can do is we can calculate the higher r value, and the value, the model, so the model with mod r closer to 1, or r squared closer to 1 if you prefer, will be better. Okay, so let's do this. So we already know the r value for the model y equals to c plus dx. This has r value 0.970. So how do we calculate the r value for the other model? Well, we come back here, we go back to stat, and remember this is the model y equals to a plus b ln x. So we want to see the relationship between y, which is in list 2, and ln x. So instead of going through and typing in ln 1.2 and all that, there's a shortcut where I can just go ln list 1. And if I key ln list 1 into list 3, it automatically defines list 3 to be the natural logarithm of the corresponding value in list 1. So now let's go back and do that same thing to calculate the r value. And now my x list, of course, is not list 1 anymore, it's now list 3. So let's see what I get. Would you look at that? My r value is now 0.995. So for the model, for y is equal to a plus b ln x, r is approximately equal to 0.995. So therefore, y is equal to a plus b ln x is the better model. Okay, so part 3 now. This is the last part of question 7. It is desired to use the given data to estimate the value of x when y is equal to 6.4. Use the regression line found in part 2 to find the required estimate and comment on the reliability of your answer. So we know that y is equal to 6.4. Right? So what am I going to do? Well, I'm going to do what they tell me, use the regression line found in part 2. So that means that 6.4 is equal to, now if you go back to your thing here, it actually tells you what your values of a and b are. So a is 1.4595 blah blah blah, b is 4.28205 blah 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 blah, right? And it's a plus b. It says x here, but we know the x list was actually ln of our x values. So these are my a and b values correspondingly. So therefore, what? Sorry, I think I actually had to determine the equation of the regression line, which I forgot to do. So that is, let me just do that in a different color. Y equals to 1.46 plus 4.30 ln x. So this is the regression line that we found, right? This is the model we're going to follow. Now, I'm not going to use these rounded values, but I am just going to write them for the sake of convenience. And then I've got this, so I can simplify and solve for x. So I'll leave that to you guys, but the answer comes out to be, using unrounded values, the answer should come out to be 3.1723 SF. So now we have to comment on the reliability of this data. So usually if I have a bivariate distribution and I'm given y, I would generally assume that the error in y is negligible and try and minimize the error in my other term, in this case ln x. However, in this case it's not too important. So in this case, because r is very close to 1, the lines of y on ln x and ln x on y almost coincide. Right? So it doesn't really matter that we didn't use the graph of ln x on y, because this means, the fact that they almost coincide means that y on ln x is a reasonable estimate. But there's one other thing I should check, and I should check whether I'm interpolating or extrapolating. But you can see here that y equals to 6.4 is within the data range. So these two facts means that the estimate is reliable. Okay, and that's question 7 done.